We now study contraction semigroups. On Hilbert spaces. So, we saw the Hill-Yoshida theorem, which can characterize the infinitesimal generator of a contraction semigroup in a Banach space. Now, if you come to a Hilbert space, it becomes even more pleasant how to check these conditions. So, we assume that V is a real Hilbert space and the inner product will be denoted by this and the norm will be denoted by this, and A infinitesimal generator of a contraction semigroup ST. Okay. So, norm ST of U is therefore less than or equal to norm of U, and therefore, this implies that ST of U minus U inner product U. So, the STU U inner product will by Cauchy-Schwarz inequality be less than or equal to norm U square, and therefore, this is less than or equal to 0. Okay. So, now if you would divide by T and T decreasing to 0, so this implies that AUU is less than or equal to 0 for all U in A and DFA. Okay. Therefore, we say that A is dissipative if AUU is less than or equal to 0 for all U in DFA. Okay. So, we say minus A will be monotone. That means AUU will be greater, minus AUU will be greater or equal to 0. Okay. So, then we also know by the Hill-Yoshida theorem this implies a range of I minus A equal to whole of V, because given any V you can invert I minus A, and therefore that is R of 1, and therefore for every range of I, in fact lambda I minus A is equal to, range of that is equal to V for all V, but anyway. So, then we say, so together these two, that is A is maximal dissipative. Why is it called maximal dissipative? That means it is dissipative and range of I minus A equal to V. Why is it called maximal? Because assume that there exists B from dB contained in V to V such that B is dissipative, range of I minus B equal to V, and dA contained in dB and B restricted to D of A equal to A. Okay. So, assume that you have these conditions. That means I am having a maximal dissipative operator, I am extending it to another operator with the same properties. Okay. So, then if U belongs to DFB, then I minus A, so there exists V in DFA such that I minus A V equals I minus B U. We have used this trick before when in the Hill-Yoshida theorem proof itself, when showing that the infinitesimal generator is in fact whatever we started with. So, then V is in DFA, therefore AV is the same as BV, and therefore I minus BV equal to I minus BV equal to I minus BU. So, I minus B V minus U equal to 0. Okay. Take the inner product with this, you get norm of v minus u square minus b v minus u equal to 0. Now, this is greater or equal to 0 and this inner product is less than or equal to 0. So, with a minus sign the whole thing becomes greater or equal to 0. So, this means norm of v minus u square equal to 0, that is v equal to u, that is u belongs to d of a. Therefore, d of a equals d of b and b equals c. Okay, so that is why it is called maximal. So, if you have the dissipativity and the range is the whole space, then automatically there is no possible extra extension with the same properties. That is why it is called a maximal dissipative properties. So, now so we have therefore, so a infinitesimal generator of contraction semigroup implies A is maximal dissipative. Now, we prove the converse. So, theorem, let A be maximal dissipative in a Hilbert space, real of course, real Hilbert space always. Okay. Then A is closed, densely defined, and for every lambda positive, lambda I minus A inverse exists and norm of lambda I minus A inverse is less than or equal to 1 over lambda. Okay. In particular, A is the infinitesimal generator of a contraction semigroup. That is by the Hilbert theorem. So, it's now you see the conditions are very easy to check. So, you just have two conditions to check, that ABB is less than or equal to 0, which is generally easy, that is just a question of integration by parts, and then you have to check that I minus A has the range is whole of V. Okay. So, proof, step 1, we will prove the density. So, let V belong to V such that uv equal to 0 for all u in D of A. So, let W in D of A be such that W minus AW equal to V. This is possible because range of I minus A is the whole of V. Okay. So, now you take the inner product with W. So, norm W square minus AWW equal to VW, but W is in D of A and therefore, this is equal to 0. Okay. So, this again this is less than or equal to 0 given to you. So, the two non-negative terms equal to 0. So, this implies that norm W equal to 0 implies W equal to 0 implies V equal to 0, and therefore, this implies that dA is dense in V, the Hahn-Banach theorem. Okay. Step 2, invertibility of I minus A. So, let u belong to D of A such that u minus AU equal to 0. Then the same thing we just saw in step 1. So, this is the same argument as in step 1. This means that u equal to 0. So, this is so I minus A is a bijection from D of A to whole of V bijection, because it is on to, and so there exists. So, given V in V, there exists a unique U such in D of A such that U minus AU equal to V. So, therefore, you have norm U square minus AUU is equal to VU less than or equal to norm V times norm U, and therefore, this implies that norm U square, this is of course less than or equal to 0. So, with a minus is less than or equal to norm V norm U, implies norm U is less than or equal to norm V. Therefore, I minus A inverse is continuous and norm of I minus A inverse is less than or equal to 1. Okay, so that proves the invertibility of I minus A. Then step 3, A closed. So, we have already seen that I minus A inverse exists implies A closed. So, we already have observed this fact, so that need not prove it again. Okay, so step 4, let lambda naught be positive such that range of lambda naught I minus A is the whole of V. In particular, we have this for lambda naught equal to 1. So, let us assume that it is the thing. So, then again you have for any V, you have lambda naught U minus AU equal to V, and therefore, this implies that norm U by the same argument take inner product with U, AUU is negative, and therefore, this is less than or equal to 1 by lambda naught norm U V. Okay. So, this implies, and also that if V is 0, then the U has to be 0. Okay. So, this implies that lambda naught I minus A inverse exists and norm lambda naught I minus A inverse is less than or equal to 1 by lambda naught. So, let now lambda be greater than or equal to 0 and V in V, and we want to solve. So, does there exist U such that lambda U minus AU equal to V. Okay. So, let me rewrite this as lambda naught U minus AU equals V minus V plus lambda naught minus lambda U. So, then U is equal to lambda naught I minus A inverse of V plus lambda naught minus lambda U. So, we are looking for a fixed point of the mapping W going to lambda naught I minus A inverse V plus lambda naught minus lambda W. So, if we have a fixed point U, that is precisely the solution of this, and then therefore, we can solve it. So, now call this f of U, f of W, and therefore, f of W1 minus f of W2 in norm is less than or equal to, so we have to subtract, the V gets cancelled out, and lambda naught minus A inverse is 1 over lambda naught into mod lambda naught minus lambda times norm W. Sorry, W1 minus W2. Okay. So, then if mod lambda naught minus lambda by lambda naught is strictly less than 1, then implies f is contraction in the sense of metric spaces implies there exists unique fixed point. So, when does this happen? So, this means that minus lambda naught less than or equal to lambda minus lambda naught less than lambda naught, and that is we have the 0 less than lambda less than 2 lambda naught. Okay. And of course, in that case lambda I minus A inverse exists as usual, and norm of lambda I minus A inverse is less than or equal to 1 by lambda. All this we have seen already in the case of lambda naught, and that is no different for any other number. So, now we know range of lambda I minus A equal to B, that is lambda naught equal to 1, implies for all lambda such that 0 less than lambda less than 2, we have range of lambda I minus A equal to B. Now, you take 3 by 2, so take lambda naught equal to 3 by 2, which is in this situation, and apply the previous step, and therefore, for all 0 less than lambda less than 3, we have range of lambda I minus A equal to B. So, in general, if you have it for any n 0 less than lambda less than n, you have range of lambda I minus A equal to B, then you can take n plus 1 by 2, okay, and therefore, you have take lambda naught equal to n plus 1 by 2, which is less than n, of course. Because 2n minus n is greater than 1, okay. And therefore, this implies that for all 0 less than lambda less than n plus 1, we have range of lambda I minus A equal to B, okay. So, this implies for every lambda we have in R, for every lambda positive, we have lambda I minus A inverse exists, and norm of lambda I minus A inverse is less than 1 by lambda, because range of lambda I minus A equal to B, okay. So, that therefore, we have proved this, okay. So, this is the proof of the theorem. So, remark. So, the importance of this theorem comes from the fact we have to only check two things. So, we need to check AVV is less than or equal to 0. This is usually integration by parts, normally done that way, okay. And for some lambda naught positive, we want to show that lambda naught I minus AV u equal to B has a unique solution for every B, okay. So, this is a combination of existence, uniqueness, and regularity theorem, okay. So, this is a single equation which we have to see, which is the type we will see in the application. This is of the type which we have seen in the previous chapter, the elliptic equations and so on, and therefore, you need to check only for that, and then it becomes obvious that it becomes the infinitesimal generator of a C0 semigroup. So, there are two important classes. One, so A is maximal dissipative, then one A is self adjoint, or 2 is minus A is also maximal dissipative. So, there are two important classes of maximal dissipative operators which we like to study because they have very nice properties, and one is that A is self adjoint and the other is when minus A is also maximal dissipative. That means A and minus A are maximal dissipative. Okay, so we will take the case A is maximal dissipative and self adjoint. So, this is the case which we would like to consider now. Okay. So, we start with a lemma. So, A is maximal dissipative and self adjoint on a Hilbert space V. Let lambda greater or equal to 0 and A lambda the Yoshida approximation. Then A lambda is also self adjoint and dissipative. So, proof, let ui belong to V, I equals 1 2, and let R lambda of ui equal to Vi. That means lambda I minus A Vi equal to ui, I equals 1 2. Okay. Now, you take R lambda u1 u2, this is equal to R lambda ui is Vi. So, this is V1 V2, which is equal to V1 U2, sorry, but U2 is what? Lambda I minus A V2. Okay, so this is V1 into lambda V1 minus A lambda V2 minus A V2. Okay, so that is equal to lambda V1 V2 minus, by self adjointness, A V1 V2, which is U1 V2, which is equal to U1 R lambda U2. Okay. So, this says that R lambda is symmetric, and of course, it is continuous linear operator, implies R lambda is self adjoint. This implies that A lambda is also self adjoint, because A lambda is nothing but lambda square R lambda minus lambda I. Okay, so therefore there is no need, it is definitely self adjoint operator. Okay, so now let R lambda u equal to V, so that again lambda I minus A V is same as u. Now, A lambda u equals lambda AR lambda u R lambda u is equal to V. So, this is lambda AVU which is equal to lambda AV, and then what is u? Lambda u minus lambda V minus AV. and that is equal to lambda square AV V minus lambda norm AV square. Now AVV is dissipative, so this is less than or equal to 0, and this is also less than or equal to 0. So this is also less than or equal to 0. Okay, so this proves this lemma. Okay, so there is one more result before with which we want to conclude. So proposition which we will use in our calculation in the main theorem next time. Okay, so V Hilbert, real Hilbert, A is in L of V, A dissipative and self-adjoint. So it is everything A lambda satisfies all these conditions. We will ultimately apply it to that. Okay. So ut equals e power ta u naught in V. So then norm of u dash t is less than or equal to 1 by t times norm of u naught for all t greater than 0. So this we have an estimate for the norm of the derivative. Okay, so proof. So you have u dash t tau equals a of u tau and u of 0 equals u 0. That is the definition, because e power ta u naught is precisely the solution of this equation here. So if I now take the inner product, so u dash tau u tau is equal to a of u tau and that is less than or equal to 0 because you have dissipativity. But this is equal to minus 1/2 or rather just 1/2 d by dt of norm u of tau square. Therefore, this means that norm of u tau is decreasing as tau increases because its derivative is less than or equal to 0. So, in particular norm of u tau is always less than or equal to norm of u 0. Okay. So, call this step 1. So, now step 2. So, let t be positive fixed. So, integral 0 to t u dash tau u tau d tau equals integral 0 to t a u tau d tau. Okay. So, this I have just integrated this equation here over t 0 to t, and therefore, this since this is my d by dt of u tau square. So, you get norm ut square minus 1/2 minus integral 0 to t a u tau d tau equal to 1/2 norm u 0 square. I have just taken it to the other side, brought this to this side and taken minus half u naught square to the other side. Okay. So, let us call this relationship as 1. Now, take scalar product with tau u dash tau and integrate. So, then you get, if you take the scalar product with this equation with tau u dash tau and integrate, you get 0 to t tau norm u dash tau square d tau minus integral 0 to t tau a u tau u dash tau d tau equal to 0. Let me call this as 2. Now A is self-adjoint, we are going to use that. We have used the dissipativity already, we have to use the self-adjoint. So d by d tau of A u tau u tau, if you use the product rule, this is A u dash tau u tau plus A u tau u dash tau. Now the A can go anywhere because it is self-adjoint, so this is equal to 2 times A u tau u tau u dash tau. So again we have that integral 0 to t tau A u tau u dash tau d tau is equal to 1/2 integral d by dt of A u tau into tau, of course, because I am just using this thing, and that by integration by parts. So 0 to t. So when I integrate by parts, I have two terms. So in the boundary, the lower term with tau equals 0 will vanish, and therefore you have t a u t minus 1/2 integral 0 to t of, then derivative with respect to tau is just 1 a u tau d tau, call this 3. So now you combine 1, 2 and 3. So 1, 2 and 3 if you combine, so 1 you have integral a u tau, okay, and here you have integral a u tau equal to something else, and then t a u tau u dash tau in terms of tau u dash tau, okay. So you have all these connections, and therefore you have, if you combine all the three and you just check the algebra, so you get half norm u t square minus t a u t plus 2 integral tau norm u dash tau square 0 to t is equal to 1/2 norm u 0 square. Now this is greater or equal to 0, minus something something is also greater or equal to 0, and therefore from these two you get that 2 times integral 0 to t tau norm u dash tau square d tau is less than or equal to 1/2 norm u 0 square. Now if you take Vt equals a dash a of Vt, sorry, if you take Vt equals u dash t, then what is the equation itself? V dash t equals a of Vt, and then V of 0 is equal to a of u 0, okay. Now a is dissipative, so by step 1 norm u dash t decreases, and it is less than norm u dash 0, okay, that is less important. So now it decreases, so if you write this from this condition, so this is 4, so 4 implies that 2 times norm u dash t square integral 0 to tau t d tau is less than to 1/2 norm u 0 square. Now this is nothing but t square by 2, and therefore this is equal to t square norm u dash t square is less than or equal to 1/2 norm u0 square. So, from this you get norm u dash t is less than or equal to 1 by root 2 times t norm u naught. Of course, that is less than or equal to 1 by t times norm u naught. The root 2 we do not bother about it, and therefore this. So, we will remember this. So, next time we will look at the problem a v u t u dash t equals a u t and u of 0 equal to u 0, and where a is maximal, dissipative and self adjoint, and then see what conclusions we can, special extra conclusions we can draw about this equation.